Okay, fire company number 2 members, we're doing a little presentation here on the new Elkhart brass nozzles. We're also going to do a little pump operator refresher training. So you should be able to see my screen right now. So in this presentation, we're going to we're going to discuss the flow requirements and formulas, uh, minimum flow for gallons per minute for attack hose lines, discuss application rate, review some pump discharge pressures and equations. We're going to go over the new Elkhart brass nozzles and do some friction loss formulas. Try to make this quick and as painless as possible. So we talk about flow. So we have to go back and understand, why we purchased this equipment, and flow has a big impact on what we do on the fire ground. So why is flow important? Because we need to absorb heat energy that's produced by the fire. So if you can look to the picture at the left, fire company number 2 members back in 1959 fire on actually on Water and Main Street. It's where the Red Roof Inn used to be. There used to be a strip of stores there, a furniture store, a few other stores. Um, you can see they're using what appears to be a 2.5-inch nozzle. So they knew back then they had to have high flow rates. So, how do we do this? We need to match the energy that's released by the fire with the amount of water that we're going to put on the fire. Uh, we can use a flow rate formula based on NFPA 1711. And it pretty much tells us for a room and contents, single family dwelling fire, we should be able to deploy 2 hand lines flowing approximately a total of 300 gallons a minute. So this would come down to about 150 GPM per hand line, which is commonly referred to as industry standard. So that's where that 150 GPM minimum flow to start a offensive fire attack in a residential type building comes from. We can look at the National Fire Academy fire flow formula. It's basically just a guideline um, to give our fire officers, incident commander, just an idea of how much water he possibly may need based on the building that the fire's in, how far the fire is advanced, that type of thing. So the National Fire Academy fire flow formula is basically area divided by 3 times percentage of involvement. So in the example down here, we have first floor, and this is based per floor. All right, so first floor, the building's 30 by 60, comes out to 1,800 square feet. Divide that by 3. So if it's a one-story ranch, about 1,800 square feet, we need to at least have 600 gallons per minute available. So in this case, it's maybe one room going, 25% involvement. Do the math, comes out to about 150 GPM. All right, and again, that's per floor, and it's only a guideline. Just if you do pre-incident planning, so you can kind of get an idea of how much water you're going to need to flow. So in this case, basics, a hose line selection and flow. So here we have a 2-story residential. I like to use this slide because there's a lot of good things going on here. But we got a fire and residential, second floor, front. So questions you need to ask. What's the area? Where's the fire at? First floor, second floor, front, rear. Who makes that decision? All right. So the officers has to make that decision. The incident commander, whoever's arriving first on scene. All right. So then, what's the percentage of involvement? So take a look at this. Um, Maybe more than 25%. Again, who makes that call? Officer decision on flow rate. So he's going to tell the pump operator, the chauffeur, as we like to use the term chauffeur, um, what line we're going to be pulling. He's going to tell the crew, which line we're going to pull. We're going to pull 1.5 inches, excuse me, 1.75 inches. I was dating myself with the 1.5 inches, 1.75 inches, or 2.5, or maybe we're using a deck gun or a blitz fire. So officer decision on flow rate. So you as the pump operator, you got to come up with the discharge pressure, right? So that's your job. Once the officer selects the attack line, flow, you have to come up with the discharge pressure as the pump operator. Quick example on this one. So we're using the flow formula. So it'll be 25 feet. The building is 25 by 50, about 1,250 feet divided by 3 gives us 416 GPM. So the first floor would be 416, second floor would be 416. Full involvement, you're looking at 800 gallons a minute. And again, this is just a guideline, all right? Nothing set in stone. Then we would need to add water for the exposures. So as an incident commander, you'd be looking at possibly needing 1,000 GPM. Not that you're going to use it all, but that's possibly what you may need for this situation. So if we did our percentage with the fire, probably like 50%. So 200 gallons a minute, thereabouts. So two good hand lines going up to the second floor, probably knock that fire out, pretty quick. So it's all about application rate. So there's a good example. A lot of you guys were at this fire. It's one of our members. We talk about application rate. We can see when the water is applied, the right application rate, how fast the fire darkens down. So I'm going to start this video and move it up to the spot that I want to look at. All right, so as this boots up here, here we go. So we're going to get we got hand lines going. But now we're going to get this deck gun going, and you can see you see how fast the fire darkens down once we start to apply, a heavy stream of water onto the fire. We start to knock down a lot of the fire, and then once we knock down a lot of the fire from the outside, we can go in and finish extinguishment with the hand lines. So there's a good example of application rate. All right, so pump operator. All right, don't be this guy. All right, and again, if you look to the left, we have our basically our pump discharge pressure formula that you need to know. Nozzle pressure plus friction loss plus device plus or minus elevation. This all comes into play. So everyone's learned this at when they've taken the pump school. And again, I've sent out a revised pump manual for everyone to take a look at, especially the pump operators. So you might want to review that. We're going to talk about the nozzles here shortly. It's going to simplify a lot of stuff. So moving on, nozzle review. All right, so here we go with the new Elkhart brass nozzles that are in service now. All right. So last year under Chief Bruce Miller, he purchased the smoothbore nozzles. The one was the Elkhart brass 2.5-inch nozzle, 1 3/16 tip. Kind of new to us because we were used to the stack tips, but I think it's a great advancement for us. I think it's going to serve us well. So again, these nozzles can be underpumped or overpumped. What we mean by that is the optimal flow is 50 psi. So the 2.5-inch nozzle at 50 psi nozzle pressure is going to give you about 295 gallons per minute. You can underpump it to get 265, or you can overpump it to get 325 GPM. He also purchased the 7/8 tip 1 3/4 nozzle, and that's going to give us 160 GPM at 50 pounds nozzle pressure, optimum flow. Again, this nozzle can be underpumped or overpumped depending on what the situation is. Moving forward this year under Chief Sears, he continued the upgrade of the nozzles, which I think is a great thing. We recently received 4 fog nozzles, Elkhart brass nozzles, and they are 160 GPM at 50 pounds nozzle pressure. So they match the smoothbore 1 3/4. So for the pump operator, you don't have to worry about what's the nozzle pressure. Is it a fog nozzle? I got 100 pounds nozzle pressure. Is it 75 pounds? Is it 50 pounds? All the nozzle pressures are the same, 50 pounds nozzle pressure. All right. That also allows us, it gives us less back pressure. So the hand line should be easier to manipulate, hold, maneuver, advance with the the nozzle person, right? With the lower pressure equals less back pressure. That said, these nozzles have to be matched as a system with fire hose. So I know we had some bad fire hose in the past. We had a lot of kinking. We did upgrade the fire hose. Most of I think all of the new 1 3/4 is Pond Supreme, double jacketed. So with these nozzles and the double jacketed fire hose, we shouldn't really have any problem with kinking anymore. So that's a good thing. So really excited about these new fog nozzles to match with the smoothbore nozzles. I think this is a great combination. All right, so we're going to see Mr. Isaacson is going to give us a real quick review on the on nozzles. So give me 1 second to set this up.
Isaacson here with the brass tacks and hard facts of weapon selection for today's fires. Understanding weapon selection for today's fires and what Andy Fredericks told us. A nozzle is to a firefighter what a rifle is to a soldier in wartime. And it is the nozzle and the firefighter who win the fight against fire. Traditionally in the fire service, we started out with a basic smoothbore, solid stream type nozzle. Still, the nozzle for today's fire service is one of the options, one of the mainstays in the American fire service. Known to be traditionally pumped at 50 psi for the tip to give you a set flow based on the size of the tip. Here I hold a 7/8 tip smoothbore at 50 psi. It roughly gives you 160 gallons a minute. But what we need to understand is that a 50 psi smoothbore nozzle can be underpumped and overpumped if you understand the tip size and the hose that's packaged with your weapon selection. Here, talking about the 7/8, I underpump it down at 40 psi. I roughly getting 140 gallons a minute. If I want to overpump it and I pump it at 60 psi, I'm roughly getting 180 gallons a minute. If I'm underpumping or overpumping, knowing how that's going to affect the reach of my stream and also how it's going to affect the kinking inside the hose lines. We talked about the 7/8 being your standard bread and butter house fire type nozzle, but we also have the very common 15/16 smoothbore at 50 psi, roughly giving us 185 gallons a minute. It too can be underpumped at 40 psi, dropping it down to roughly 160 gallons a minute, or overpumping it at 60 and getting somewhere around 200 gallons a minute. The key factor is just with the 7/8 is when we underpump it, how's it going to affect your hose and nozzle package in the relation to kinking on the fire ground. So let's move on to the bigger nozzle for more of a commercial fire attack or a standpipe operation, the 2.5-inch smoothbore. That, once again, is still traditionally known as a 50 psi, but it too can be pumped at 40 or 60. The 2.5-inch nozzle, historically speaking, had the triple stack on it with the 1 inch, the 1.125, the 1.25. What I hold here today is the 1 3/16 tip, which roughly is 300 gallons a minute at 50 psi nozzle pressure. When underpumped at 40, is going to give you closer to that 1.125 tip at 265 roughly. And if you overpump it, it's going to give you that 1.25 at 325. Next on our weapon selection, we're going to talk about the automatic or constant pressure nozzle that's been in the fire service for a little over 40 years. The automatic nozzle definitely has a place in a fire service. It's a nozzle that constantly gives us a good reach and stream, and the good reach is one of our top threes that we need. It's like the thumb over a garden hose. The more pressure you apply to the tip of the garden hose, the longer the reach in the stream is. And what we have instead of a thumb is we have the spring here inside the automatic nozzle that when no water is applied or no pressure is applied, the spring is fully elongated. As we up the RPMs on the apparatus and apply more pressure, the spring will compress, allowing the flow range to go to a higher range. So the automatic nozzle will flow large amounts of water if the proper pressure is applied to it. But if for some reason we have a water supply issue and we have exposure issues at low water supplies, we can still have that stream reaching the objective, it being exposure to provide proper water on the exposure itself. Another reason an automatic should be on all apparatus as an option, maybe not always pre-connected to your house fire attack line, but for foam operations. The automatic nozzle is a great nozzle when we're talking about creating foam and being able to match it up with the foam given for your actual apparatus. The automatic nozzle is a great nozzle when we're trying to apply water to large number of exposures at a reduced water supply option. So understanding that the automatic nozzle is a variable flow nozzle with a constant pressure based on the spring itself. Next to the automatic, we have the fixed gallonage or constant gallonage. I hold here is a 150 at 50. As you can see, side by side to the automatic, there's not a spring. There's just a set stem in here that when water is applied opens to a certain distance to allow a given flow at whatever pressure. This is at 150 at 50. You can change these stems out. Could be a 150 at 75 or a 175 at 75, 200 at 75. So you have a constant or fixed flow nozzle that you can change its flow and pressure by basically just changing out this stem. I look at a fixed or constant gallonage when you talk about a 150 at 50 right here being comparable in the mainstay of the fire service. I call this a traditional mainstay nozzle of the fire service. When I put this chief nozzle, the 150 at 50, next to the 7/8, this 150 at 50 gives you a variable streams. You can have a straight stream, or a wide fog pattern, or a narrow fog pattern at 150 at 50. So it too is a nozzle that will give you that 150 gallons a minute, which is the accepted, understood minimum flow for today's interior fire attack, but gives you that ability to apply a fog stream, as where a smooth bore will not give you a fog stream. So these two nozzles, when we talk about interior fire attack on today and tomorrow's fires, both at 50 psi nozzle pressure will achieve that 150 GPM as a minimum for today's fires. So moving on to the other nozzle would be a selecto gallonage nozzle. This one here has a range from 30 to 200. So once again, it too does not manufacture water. None of these nozzles manufacture water. It requires an understanding of what the pump discharge pressure will give based on the length of hose when it comes out the end of the nozzle. So understanding that if I have a required low flow, that the pump operator knows that I'm trying to achieve a 30 GPM flow. If I dial up, just because I dial up to 200, I'm not going to guarantee get 200 gallons a minute without communicating with the driver engineer, pumping that based on understanding the friction loss for the hose to get 200 GPM out the end of a selecto gallonage nozzle. The one thing I like to say when I'm talking to somebody about nozzles and weapon selection, the big three. What is the desired amount trying to achieve at your fire? Is it 150? Is it 300? What is it? The desired amount being number one. Two, that desired amount's got to reach your objective. You got to get that water on the burning solid fuels if it's an interior fire attack. So what's the reach of the stream at a given pressure? When we're talking about under pumping it at 40, what's that reach going to be? Is it still going to have the flow, and is it going to have the reach that you need? And lastly, the one that still is very important is what's the nozzle reaction? What is the combat mobility of it? Is it a nozzle reaction so high that you're not going to be able to move beyond the threshold of the front door, move down that hallway, and get water to the seat of the fire? So understand the 1, 2, 3, the desired amount, the desired reach, and the desired nozzle reaction to give you a nozzle hose package that will get water on your next fire.
Okay, so that was Mr. Isaacson talking about nozzles. Real quick on the automatic nozzle. We used to use the task force tip nozzles, which were automatic nozzles. Some of our departments still use the automatic nozzles. Some of the big issues with those, because the way that the nozzle is designed, you get a good looking stream. Unfortunately, you could be 30, 40, 50 gallons under what you should be flowing, and really have no idea that you are not producing an effective fire attack stream. So that's one of the drawbacks to the automatic nozzle. All right, so we're talking a little bit about friction loss calculations. So if we look at IFSTA formula for friction loss, this is an example of our 1 3/4 hose flow at 160 GPM. We use a coefficient formula with ISTA. It's usually the coefficient times the gallons per minute squared times the length of the hose line. So in this case, coefficient for inch and three quarter, well, the flow to get the gallons per minute, Q, which is the gallons per minute, is divided by 100, so we come out to 1.6. So 1.6 times 1.6 is 2.65, and then the coefficient from ISTA is 15.5. So the friction loss in this case would be 78 psi per 100 for a 200-foot hose length. The problem with the coefficients is they were developed years ago, and with the advance in technology in fire hose, different types of fire hose, the coefficients are different for every um, type hose manufacturer. So unless you go out and do your own fire flow testing to get your coefficients, you really can't depend on the ISTA formula. So I know we went out last year, we did some fire flow testing. We came up with some new coefficients for our inch and three-quarter hose and for our 2.5 inch hose. I recently contacted American Hose Company, which is our vendor for our Pond Supreme. They did send me a list of coefficients for their hose, and we are like right on the money with our hose testing with the coefficients that the manufacturer sent us. So going forward, so this when this in this problem, the pump discharge pressure would be 128 psi. All right, so here's our friction loss flow testing that we did. So again, our Pond Supreme, and let me put this pointer up here. All right, so here's our inch and three-quarter Pond Supreme. All right, this is the coefficient we came up with. Instead of 15.5, we came up with a coefficient of 10. The 2.5 inch hose, which is the Key Echo 10, we came up with a coefficient of 1.5 instead of a coefficient of 2. So the friction loss is much less um, based on our hose testing than using ISTA formula, right? So here's a friction loss calculation using our test formula, our coefficient, all right? So you can see we crossed out the stuff on the bottom here, the ISTA coefficients. So with this illustration, we can see that using the ISTA formula, all right, stays the same. That stays the same. Now we're going to substitute our friction loss formula, our coefficient, and we're going to come up with a 50 psi friction loss for this illustration, 200 feet of inch and three-quarter flowing 160 GPM. So our pump discharge pressure is going to be 100. So if the pump operator flows 100 psi through our pre-connect right now with either our new fog nozzles or our 7/8 tip smoothbore, you're going to get the correct flow of 160 gallons per minute. So here is the rule of thumb formula that we taught for years, and it's still effective if you if you forget. So I did the illustration here using our 200-foot pre-connect flowing 160 GPM. Again, it doesn't now because we have the new nozzles. It doesn't matter if it's a fog nozzle or if it's a smoothbore nozzle. We can use the hand method, and looking at our hand method of 150 GPM probably comes the closest to our actual friction loss pressure using our coefficient. So if we use the hand method, so that would be 3 times 10 is 30, so friction loss for every 100 feet would be 30 psi. So in this illustration with this problem, we would come up with a friction loss of 60 psi and nozzle pressure of 50, so we'd be at 110. Using our coefficient, we said our pump discharge pressure would be 100, so we're really not that far off with using the hand method for inch and three-quarter. All right, going to the 2.5. All right, again, we can under pump, over pump our inch and 3/16 line. In this case, we're using 200. I should have changed this to 250 feet of 2.5 inch hose using 295. So using our formula, IFSTA formula, all right, our IFSTA formula would give us, and again, I changed it down here. I changed the calculation down here to 250 feet. All right, this should have said 250 feet because our pre-connect is 250 feet or 2.5. But using the IFSTA formula at with their coefficient of 2, we would come up with a friction loss of 43 psi. Right. Using our friction loss coefficient, going down to using 1.5 instead of 2, we would come up with a friction loss of 32 psi for 250 feet of 2.5 inch of the pre-connect. And in a rule of thumb, we used to teach the rule of thumb. We still teach the rule of thumb, which um, throws us off a little bit. So if you're using the drop 10 method, in this case 250 feet of 2.5 inch hose flowing 295 gallons a minute, drop the 5 minus 10, it leaves us 19, so the friction loss is 47. So in this case, the if we compared our actual numbers using our coefficient to the rule of thumb calculation, there's approximately a 15-pound difference in friction loss. So that 15 pounds is going to really throw you off as a pump operator. It's going to also add a lot more water coming out the nozzle than you think. So the rule of thumb here kind of is out the window because of the friction loss calculations that we did. All right. So Elkhart Brass, if you go on your phone, you can go into their app. They got a great app for nozzle reaction, fire flow, pump discharge pressure, friction loss, that type of thing. So you can just look under. That's what it looks like when you download the app. It's free. It's a great resource. All right. So flow from orifice. We talk a lot about the flow that comes out of the smoothbore nozzles. Um, this is just to give you an idea of where it comes from. There is a formula for it. That's a rule of thumb formula. 30 times the diameter squared times the square root of the nozzle pressure gives you the gallons per minute. So with the 7/8 inch tip, this is where we come up with the 160 GPM. So some nozzle calculations: 15/16 tip, same calculation, gives us 185 GPM. And the inch and 3/16 tip, using a 50-pound nozzle pressure, that's where we get 292. We can round it up to 295. And for the pump operators, we talk about evaluating our water supply. So here's our compound gauge. So it's kind of important that you take as a pump operator, if you're taking a feed from a hydrant, try to get the static pressure. So the static pressure is no water flowing, so we're not flowing anything yet. So in this case, our static pressure is 70, right? We get water flowing. Our first line over here is a inch and 3/4 flowing 150 GPM. Our compound gauge drops down to 60. That gives us a 14% drop from static to residual, which there is a formula for that. It's not something you're really going to use on the fire ground, but basically that tells us in this situation we could put out 3 more times the original flow. So in this example, we'd be able to flow 450 GPM from our water supply. The big takeaway here is, as a pump operator, if you can get your static pressure when you first get a water supply from a hydrant, whatever the first line is, take a look at the drop. Once you get water flowing, try to get an idea of what the drop was on your compound gauge from static to residual pressure. Now, if you're putting out a small line, like we're putting out here, and you have a big drop, a drastic drop in your compound gauge, there's an issue with your water flow. You're either on a bad hydrant, there's a blockage somewhere in the line, there's a valve partially shut, something's going on. But if my first line going out is my deck gun, so if I put 500 GPM out the deck gun for a blitz attack, I expect a big drop in my compound gauge from static to residual. So just a couple things to keep in mind as a pump operator. So what we can do is know your flows. Okay, know your nozzles, know your flows. Determine your hose coefficients, which we did. create a flow chart, which I did. I have 2 new flow charts, which will be put on the apparatus. So flow charts represent the new nozzles. All right, we don't want that. Sorry about that. We have to go back where we were. All right, then label your discharge. You can label your discharges with required pump discharge pressures for the pump operators. Since most of the time, most of our fires are pre-connected hand lines, we don't add extra hose. Just something for the officers to think about if they want to do some type of labeling thing to make it a little easier. So here's the pump chart that we designed for the engines. All right, so 1 3/4 hand line, smooth bore in red, 1 3/4 fog nozzle in blue. They're the same. All the pressures are the same. There's a chart for the 2.5-inch hand line, and there's a chart for the bumper hand line, because the bumper hand line is 100 foot. So these charts will be on the engines relatively soon, so the pump operators can take a look at them. Initial flow. Okay, initial flows. So we can see that our initial flows are using the 50 pounds nozzle pressure. So 160 with the 2.5, it's 295. So for you pump operators, here's a little problem. So 200 feet, 1 3/4, our new fog nozzle, 160 gallons per minute pre-connect. All right, so the nozzle pressure is 50. Friction loss with our coefficient in our chart comes out to 25 per 100. So we have 200 foot of 1 3/4, so the friction loss is 50. So our pump discharge pressure is 100 psi. Okay, same thing flow in the smooth bore. Nozzle pressure is the same layout, same flow. Friction loss is the same. That's the nice thing about getting these nozzles matched, the fog nozzles and the smooth bore nozzles. And pump discharge pressure is 100 psi. All right. Rule of thumb calculation for the inch and 3/16, 2.5. All right, 250 feet, 50 psi. We use our friction loss formula or drop 10 method. We come out with a 97 psi if we use the rule of thumb method. Next slide, you're going to see an issue with that. So if we use our flow chart, which is based on our coefficient for our 2.5, nozzle pressures 50 psi, friction loss is actually less, it's 30. So our pump discharge pressure is 80 psi. So there's basically a 17 to 20 psi difference between what we should be flowing and what the rule of thumb gives us. So that could be a big difference in flow, water flow. So you'd be flowing a lot more water than you think. Could become an issue for the firefighters holding on to the hand line. So just bear that in mind. Try to use the flow chart. Try to review it. So any questions, there's my info. Hopefully we'll be able to get out in the field soon to do some training. So for now, have a good day.